This lesson is entitled Linear Approximation. Linear meaning straight line, and approximation means not the answer, but a close guess, if you will, but it's more than a guess at what the true answer is. We introduced this lecture with more or less a prologue, in other words, a review of some things that we've already talked about in previous sections of calculus before you got to this point. Of course, this lesson is based on the fact that, or predicated on the fact that you know how to find simple derivatives, and that you know how to write the equation of a straight line given the slope and a point, which is pretty much introduction to Algebra 1. So let's begin. Let's start by asking a few questions. Question 1, if f of x is x to the fifth, what is f of 2? Of course, we know that if f of x is x to the fifth, f of 2 means put 2 in the place of x and do the math. And so it's 2 to the fifth power, which is 32, which is pretty simple to do. Let's look at question 2 here. Suppose we have this function, and we'll call it capital L of x, and suppose it's 80x minus 128. Now you might say, where did you get that from? Actually, you're capable of getting that for yourself. We'll see that in a minute. But for right now, we're simply putting it here. This function, L of x, is 80x minus 128, and we're asked the question, what is L of 2? That is, what is the value of this function when x is 2? So it's 80 times 2 minus 128, which is 32. Now, what are we doing here? What are we trying to get across? Well, when we put 2 into this function, we got 32, but it was a little bit of arithmetic involved. You had to know that what 2 multiplied by itself 5 times is. Here, somebody that has basic skills in just arithmetic and doesn't understand anything about exponents or whatever, they can work this problem and get the same answer. So this is what we've done is we have a straight line equation that gives us the answer. And the same answer is when we put the value into a fifth degree polynomial, okay? So let's go to question 3. What if you were given f of x equals x to the fifth? Yes, that's our first function. And you were asked to find f of 1.987. Well, that means 1.987 to the fifth power, or 1.987 multiplied by itself 5 times. Now, that's not a real problem for us, is it? Because we grab our calculator and we either multiply 1.987 by itself 5 times or raise 1.987 to the fifth power. Either way, we get an answer of about 30.97. That's rounded to the nearest hundredths place. Of course, without a calculator, that's not an easy problem to do, is it? And that's one of the things we want to drive home in this lesson, that there's a lot of work involved. Let's go to question 4. Let's take that same function, L of x is 80x minus 128, and let's put 1.987 into that. Now that's 80 times 1.987, but that's not really difficult to do. Not like multiplying 1.987 by itself 5 times. So we can all pretty much agree that 80 times 1.987 is doable, and subtract 128 from that, and we get 30.96. So that's doable. That's doable. Whereas multiplying it by itself 5 times is not really doable. So what we have here is we have an equation that gives us an answer that's almost the exact answer that you get with the calculator, with a little bit of work. So if you were stranded without a calculator, you have a way to find out what 1.987 is to the fifth power without having to do a lot of work. And that's what we want to drive home in this lesson. Was any of the previous 4 questions more difficult than the others? And the answer is yes. Question 3 was it because we needed a calculator? Yes, it was, or be willing to do a lot of work. Why do questions 1 and 2 have the same answer? We're going to explain that in just a minute. And why do questions 3 and 4 have not exactly the same answer, but very close to each other? So on the next slide, we're going to look at the graph of the line tangent to the function f of x equals x to the fifth at the point 2, 32. Now you should know how to do this from earlier sections of your calculus course. In other words, we have the point 2, 32, and if we weren't given a 32 and only given 2, we can find the 32 rather easily. So to write the equation of a line, earlier you learned that you need a point and the slope. Well, we have a point, 2, 32. X is 2, y is 32. Can we find the slope? Well, of course we can. Now, maybe we couldn't when we first walked in the door of a calculus class, but now we can. That's 5x to the fourth, and that's the derivative or slope, and so you can find the slope by simply 5 times 2 to the fourth power, which I believe is 80. Okay. Here's the graph of the function. The red graph you see here is the function y equals x to the fifth. And the blue graph is the slope of the line tangent to the graph at 2, 32. As I said, that's the equation. That's the line that you would get if you found the slope of the line, take the point 2, 32, put it into the point slope formula, y minus the y coordinate equals m times x minus the x coordinate from algebra 1, and graph that, solve for y and graph that function. Now, we see that, of course, this line, the dotted line, is tangent to it at 2. That means that it touches there. That's why the answer, when you put it into 2, into the linear function and into x to the fifth, gave you the same answer, because they are the same point on each of the graphs. On the other hand, when we take the line point 1.987, and that's located here, it is not at 2, 32, but it is so close that the two, for all intents and purposes, are the same. In other words, the blue line, the tangent line, and the curved line, the red line, are, for intents and purposes, the same from, say, somewhere around 1.8, 1.9, all the way up to maybe here, something like 2.2 or 4, somewhere around there. They're the same. Now, obviously, after you get, they only stay the same for a while, and then the two graphs diverge. They have nothing in common, okay? And that's okay with us, because we're only interested in the graph near 2, because 1.987 is close to 2. Now, this is just a rehash of what we've said earlier in the course of how to write the equation of a line tangent to the graph. If you're given a function, f of x, and you're given some point, x is equal to a, and you're asked to write the equation of the line tangent to the f of x at x equal a, what do? Well, first of all, you need the y coordinate. Well, we can find the y coordinate. If x is a, the y coordinate is f of a, is it not? And you need the slope. Well, the function is f of x, the slope m is f prime of x. So we want it at a, so it's f prime of a. So we have the slope and we have the point, and so we can substitute in to our function here for m, f prime of a, and for y sub 1, f of a, and for x sub 1, a, and solve for y. Okay, so that's what we would do. And if we solve for y, we're going to get this. Okay, if we solve for y, we're going to get this. Now, most textbooks have a special formula that they have a way of writing it, and which is, they call it L of x. That's why earlier we called our linear equation L of x. So many books use this formula. We're going to use it, but you really can get by without using this formula if you can only get to this step up here, substitute in and solve for y. And that's a lot less memory work to do. So that is up to you if you want to use this special formula for writing the equation of the line, tangent the graph. So many textbooks have that we're going to go along with it in this particular lesson. Okay. So here's just a schematic of what we've just displayed here. If you have a function, some function, f of x, and L of x is the tangent line, this is what it looks like, okay? And they are one and the same where they meet. So this graph would be very, this function would be a close approximation of this function right here, and for anywhere from about here to down here, but then the two lines no longer seem to be close to each other, and it would not be a good way to approximate the answer. Let's take an example here. Use the technique of a linear approximation to find the square root of 10.5, and then let's also find the square root of 7.8. Now, we're two parts to this. Why? Well, that's going to be self-explained as we go along. First of all, I don't know the square root of 10.5. I can find it with my calculator. I don't know the square root of 7.8. I can find that with my calculator. But let's imagine not having a calculator. So the first thing we want to do is we want to decide on a function that we're going to use. And since it's asking for square root of a number, let's use f of x as the square root of x as our equation, our model function. That seems rather obvious. Now, the second thing, we don't know the square root of 10.5. Do we know the square root of a number that's close to 10.5? And the answer is yes, 9. We know the square root of 9 is 3. So let's take that fact. In other words, let's take the function f of x is the square root of x, and x equals 9, and let's write the equation of the tangent line. Now, the first thing we need is the y coordinate. Well, since we know that the square root of 9 is 3, 9 is relatively close to both of these, so we have that they are going to, we're going to explore it here, and we have that we know that the square root of 9 is 3. These are my y coordinate, here's my x coordinate, so we need the slope. We need the slope, we got the x coordinate, we have our y coordinate, we take the derivative, and this is x to the 1/2 power, so we take the derivative, we get 1 over 2 square roots of x. We want to find out what it is when you put in 9, so that's 1 over 2 times the square root of 9, or 1/6. So that means that y minus the y coordinate is this slope, 1/3 times x minus the x coordinate, or if we put it in the form of this, it looks like this. That's the equation of the line that we're talking about that's tangent to the graph at that point. So we're writing it again, rewriting it, taking out the y so that it's, those of you that might be learning this and plugging into the Lx equation, we'll do that for you here. So this is the function. The only difference between this and this, that we've put it instead of a y, we've written it as an ln of x. Okay. Now, what do we want? We want the square root of 10.5. Well, this is an equation right here that is tangent to y equals the square root of x at 3. So we want it for 10.5, or for 9, x equals 9, excuse me. Well, we are going to see what we get for an answer when we put 10.5 into this linear equation. And so all I do is I do this, I subtract the 9 from the 10.5, that's doable. I take 1/6 of that, that's doable, and add that to 3, that's doable, and I get 3.25. In other words, that's my approximation of the answer. That's not the answer, though. Here's the actual answer if you use a calculator. But look how close our guess is, our approximation is to the exact answer. Pretty good. Now, we want to find the square of 7.8. Well, what's a number close to 7.8 that's a perfect square? And that also is 9. So this same equation that we have here will serve to find L of 7.8. So what we're going to do is do that. We're not going to rework this problem. We're simply going to put 7.8 in, and we do the arithmetic, and we get 2.8. And if we use a calculator, look what we get. So this, our close answer, approximation, is very close to the exact answer. Now, the reason we did both of these is to drive home the point. What if you wanted the square root of 10.3? You could use the same setup for finding the square root of 10.3 or anything in the area of 9, okay? So that's what we're trying to drive home here. We get 2 for the price of 1 because both of these numbers are close to 9. This is slightly bigger. This is slightly small, okay? Are we close enough to declare they're the same? Well, it looked like by the answers we had there, but now let's look at the graph. Look at the graph of the function. The blue function is our straight line. The red function that you see is the square root of x. And here's our point right here, 9, 3. And here's on that graph, 10.5 and its y coordinate, and 7.8. Now look how close these two are. They all, in other words, this red line and this blue line are pretty much the same from here up to about somewhere around maybe here. In other words, we could find the square root of any number as long as it was somewhere between, say, 5.2 or in that area. I'm sorry, 6, around 6 is not 5.2. This looks like this would be 6. So somewhere 6, certainly 7 on up to, say, maybe 12, something like that. I'm just eyeballing that here, okay? And so, are you catching on to what we're doing? Now you may be saying, well, we could have been doing this all along. I mean, we knew this earlier. We did. Why was it not addressed earlier? Well, we just wanted to do something with it at that time. We wanted to get deeper into the calculus, maybe to explore this more deeply as we are here. I said, so furthermore, it appears this graph would be probably good from anything x from, say, 7 up to 13 as we look back. 7 up to about 13, probably pretty good, but that's all we could. It wouldn't be good for 4.8, because where is 4.8? Well, 4.8 is back here somewhere, okay? And they've diverged. And so it wouldn't be good for that, nor would it be good for 15.2, because 15.2 is up here and they begin to diverge there. So I hope you understand what we're trying to drive home here. So for a summary, the thing you've got to remember in doing this is you've got to choose a function that models well what you're looking for. In the case of the previous example, that was the square root of x. And your goal is to find f of c, that is the value of the function at c. So you're going to choose as your model, and put into your model some number that's close to c, that you know f of a of it is. And so we do that. Once we choose our function and once we find the number that works, then we find our y-coordinate by putting a into the function. Then we find the slope by putting a into the derivative of this function. And then we simply plug in our f of a here, our slope here, and our a here. And then we are ready to go. Okay. And then we can find what L of C is, which means that everywhere there is an X, when there's only one X in this function, we put in C and we do the arithmetic. Practice will make you see that this is very doable. And once you get the hang of it, you'll have that hopefully as part of your learning that you've probably put away and say, I've done that. Let's take another example here because we've got the time to practice a little bit more here. We need to practice. Let's take 3.875 squared. Now you could do that without a calculator. That's not too difficult to multiply 4-digit number times a 4-digit number, but at any rate, we're interested in finding it without a calculator. So what's our function going to be? F of x is x squared. That's your first thing. Choose your function. What's a number close to 3.875 that you can square it easily? 4. Okay. So when x is 4, then y is 16. There's your y coordinate. So we have our x coordinate. We have our y coordinate. We take the derivative of x squared, which is 2x. We find the slope at x equals 4, and that's going to be 8. And so we take our equation here, and what we're going to do is in the place of f of a, we'll put our y coordinate, which is 16. And in the place of a, we'll put in our x coordinate, which is 4. And in the place of f prime of a, we're going to put our slope, which is 8. So now all we have to do, we have it. So all we've got to do is now to find 3.875 is to put 3.875 in for x. And then we do the arithmetic. That's easy enough. Times 8. That's easy enough. And add to 16. That's easy enough. We get 15 when rounded. That's rounded answer, but it rounded to 15. And here's the exact answer. So we're in, looks like, great shape there. This is what this looks like from a graphic point of view. This is y equals x squared. And this is that function we just found here. What function is that? That's your functions 16 plus 8x minus 4. That's the graph of the straight line. And look how close those two. This is the point we know. This is the point we want. And this is why it works, because they're so close together. In fact, these two graphs seem to be close together from where my hand is here, somewhere up to here. Okay, that would not be good if you were looking for find a number squared that were up in this region. In other words, somewhere around 6 or whatever. So take that for what it's worth. Let's look at example 3. What we want to do here is take one that's not so nice without a calculator. In other words, the others we could do if we were willing to put in the time, we can get the answer. But what if you want the sine of 0.4? And suppose you didn't have a calculator. You were in a situation where you have no calculator and you had to find the sine of 0.4, i.e. you're on a test or something, whatever. How would linear approximation work? Well, we obviously know our model function is going to be the sine of x. Now, what's a point close to 0.4 that we know the sine of? Well, pi over 6. Pi, remember, is about 3.14, or let's say 3 divided by 6 is a half, 0.5. So we're going to use 0.6 as our known. So we have x is pi over 6. So the sine of pi over 6 is 1/2. So there's my y coordinate. Okay. Now I need slope. Well, the derivative of the sine is the cosine. And the cosine of pi over 6 is the square root of 3/2. So we've got everything we need. In other words, f of a, which is our y coordinate, is 1/2. F prime of a, which is our slope, is the square root of 3/2. And a, which is x coordinate, is pi over 6. So there's our equation. And we simply put pi over 0.4, 0.4 in for x. And we have to do the arithmetic. Okay. But if we had a calculator that didn't, say we had a full function calculator or one that had a square root key on it, and we could do this. We could do this. We don't have to have a scientific calculator to do this particular problem. Of course, this is a hard sell to make to a lot of students because we live in a world of calculators. There's the graph of that function, and you can see how close those are together as well. Remember, these graphs that you're looking at are under the microscope. We have zeroed in on them to blow them up so that we could make them presentable so that we can discuss the facts that we're trying to drive home. Okay. Concluding remarks. One reason for this lesson is to demonstrate why you were taught earlier the concept of equation of a tangent line. In other words, probably when you learned the power rule, my guess is, but I wasn't there in your class, so you studied that, but more than likely you immediately had some problems that ask you to write the equation of a line tangent to the graph with your first derivative formula. Okay. To allow you to see historically why early mathematicians would be interested. In other words, they did not have a calculator. Okay? They had tables they had to use. They had logarithms that they could use. This is one of many tools that they had in that toolbox if they had to do a problem that was labor intensive. And this was, for early mathematicians, was very helpful. They created trig tables, tables of trig functions, so that if you wanted to find a sine of 0.4, you went to a table. So they used something of this nature to create this table. Calculators have made this process somewhat moot, but not the concept. If you are in programming and you need to write a program that maybe, let's say, sets up or creates a table of trig values, this might be handy. You see, programmers need a menu, they need formulas. And so we say, hint, hint, just possibly it could be something that's important for you to need to know, not only useful, but necessary. Let's close with, we want to take one last problem just to say, let's go through it quickly. Let's not do any thinking on this, and let's not have any particular formula. So I want to find 2.87 to the fourth power, and I want to do it without a calculator. So what's my model function? X to the fourth, that's no secret. What's a number that you can raise to the fourth power that's close to 2.87? That's 3. When x is 3, what is y? Well, 3 to the fourth power is 81. That's my y coordinate. Here's my x coordinate. If I take the derivative, x to the fourth, that's easy, 4x cubed. If I put 3 into it, I get 108. There's my slope. So I put in y minus a y coordinate is the slope times x minus the x coordinate. And if I, this is my formula that I can use now if I want to find 2.87 to the fourth power. I simply put 2.87 into this and do the arithmetic, and I get this, 66.96. Now, the actual answer is 67.85, rounded to the nearest hundredth place. You might say that's not close, and you're right, it's not. You see, 2.87 is not real close to 3. You say, well, it is, but not like, and then you're also doing it to the fourth power, okay? Now, in that earlier problem that we did, the reason it works so well, we wanted to find 1.987 to the fifth power. 1.987 is very close to 2. 2.87 is not all that close to 3 in the scheme of things, considering the function. So we do have some discrepancy as far as closeness of answer here, but that's not why we were running through this. We're not interested in the answer. We're interested in you, A, find the function, B, find the value for x, C, find the slope for that value of x, and then put it into your function and then do the arithmetic. So that's really all we have this problem to do, is to demonstrate for you that there's a rhythm to this, and bang, 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 you can get the answer quick. So we wanted to end on an easy note, give you some confidence, so that if you have problems, just think of this and run through this. And you already know from Algebra 1, your point slope formula, you already know earlier that derivative, first derivative is slope, and you're well on your way. So this concludes this particular lesson.